MCAT stands for Micro Cross Arm Tester. And that's exactly what the product's about. It's about looking for leaky insulators on 11 kV systems, and identifying if you've got if you've got a leaky insulator, and B, how to locate it. So as I said, that's the whole idea of this product, is to look at 11 kV pole mounted systems. And what we're going to do this morning is I'm going to explain why 11 kV wooden pole mounted systems are different to either concrete or metal systems. The idea of this product, as I said, is to check the voltage on the cross arm. So it will be looking at, we'll be attaching to the cross arm itself and checking if voltage is present. If voltage is present, we then look to calculate the milliamp leakage level, which gives us the voltage together with the milliamp leakage level will give us an indication as to the danger level that the system poses at that point. And then we would look to locate which of the three insulators attached to that system has actually gone down. So as I say, what we're going to do this morning is to start off looking at what is an 11 kV pole mounted system. If you look at any mounted system that's made of concrete or metal, you'll find that they're earthed out. So if an insulator broke down, and even if it only partially breaks down, invariably what it'll do is take out the system. The idea of a wooden pole system is very different on that front, because the actual pole itself is unearthed. Now the pole has a resistance to ground from the cross arm that you can see at the top here. Hopefully you can all see my indicator there showing that cross member, but you'll have a metal cross member that will be attached to the wooden pole, and then the system itself, the 11 kV cabling, will be mounted on top of the insulators which carry it from A to B. The whole idea of this system is the pole itself will be somewhere between 80 and 40 megaohms. So that means if an insulator partially breaks down, the system can hold up and still be, still be live and still be useful to us, as in carrying our electricity. But obviously, if you've got an insulator that's broken down, you want to know that that's broken down, and you will have an indication in the substation that there is a leakage going on. But it will allow the system to still carry on working whilst you find that faulty insulator. Now, insulators, generally speaking, they either go completely or they start to leak to earth. And when they start to leak to earth gradually, they will get worse over time. And that may be because the insulator has cracked, has got impurities in it which have broken down over time, or it could be physical damage that's happened to that insulator due to weather, maybe, or animal attacks or whatever. But if the insulator hasn't fully broken down, the system will hold up and, as I said, deliver electricity. So the whole point of this unit is when somebody is working on the poles, they need to know, is that cross member live? And if it is, what level of danger that presents. And that's what this unit will do. So, as I said, the insulator itself can break down and the system can remain in service because the pole itself acts as an insulator, or an additional insulator. But it does mean the cross arm and the pole therefore can have potential voltage, and therefore pose a problem for the person working upon the systems. And so the MCAT itself is our solution to locating leaky insulators on such type systems. This is the MCAT, how it looks. It's built into the actual unit itself, is built into a very strong case, and the case itself, when the lid's shut, it'll be IP67 rated. There's nothing in the case of this instrument that is done to the case to change the IP rating, so this unit can be carried around in all sorts of weathers, and would be in theory, if you dropped it into a lake or a river, it will float if the lid's shut. So there's several steps for using the MCAT, and these have to be carried out in the following order for safety reasons. If they're not carried out in the correct order, then that could pose an issue for people working upon the systems. And the MCAT itself, it's been derived that it will lead you to the order that you need to do things. So the first step you need to do is connect the earth lead to the instrument. The other end of the earth, so you basically plug the earth lead in and do it up. The other end of the earth is left unconnected for now, but the unit will not turn on if you haven't connected the earth lead to the unit. You then connect the HV probe to the unit, and again you leave that so that it's not connected to anything, it's floating if you like, and at that point you can switch on the MCAT plus. Now the unit then will carry out you carry out a self test. So what the unit does is it checks all its wiring, all its connections, and makes sure that it's happy with everything. So the HV probe and the earth lead should not be connected or touching any earthed point or anything. It needs to be floating. Once you carry out that test, in theory, the unit will then display probe OK, and that's telling you that it's done a test, it's looked at the wiring, its internal wiring, checked all its connections and checked itself as it were, and found it to be OK, and it will display, as I said, probe OK, and then you can proceed to the next step. So the next step is dealing with the still work voltage, and as we said earlier, as I described, the wooden pole will have normally a steel cross member attached to the pole itself. That steel cross member is not earthed, and therefore that pole is not earthed other than it being buried in the ground itself. So between the cross member and the ground, as we said, you've got somewhere between 8 and 40 mega ohms of resistance. Now that depends on the age of the pole, the condition of the pole, the temperature, the humidity, participation. They will all have an effect on the resistance of that wooden pole, but essentially you're going to have a pole that is acting as an insulator. So with our unit then, going back to that, we connect the earth now to a known earth, or we make a temporary earth. Now the unit comes with these little pegs, so if there's no known earth that you can connect to, you can put a peg into the ground and make a temporary earth and connect your earth to that. You then take the probe and you hang that on the steel cross arm. Now the probe itself is terminated at the top end with a little hook. So you hook the probe over the steel cross arm. Now the probe is essentially made as a Bowthorpe rod, and anybody working upon these sort of systems would generally be speaking have their earth rods that they use for earthing out when they're working, and they would use those rods to attach the probe to the steel crossarm. So going into the unit, we look at the menu and we select from the menu the box that says still work voltage. The unit, and then you hit OK, and the unit will then measure the still work voltage. If 0.3 kV or more is detected, then the V present will light. So if more than 300 volts is present, that's when the light will light up. To give you a caution, to tell you that there is voltage there on that cross member and you need to be aware of it. If the kV is greater than 2.7 kV, then a buzzer will also sound and the ISC function will not be allowed. Essentially, if you've got more than 2.7 kV there, you have got a significant problem. So there's no point measuring the potential milliamps because it's irrelevant. You know that if the voltage is greater than 2.7 kV, then you need to take due precautions, and it will be treated as a live situation. A danger sign is shown upon the display and a phase test can be carried out. So we'll be getting to the phase test in a minute, but at that point, so the first point you're doing, you're connecting up the probe to the cross member, you're checking the cross member's voltage, and if the voltage is less than 300 volts, then all is great. You don't need to do anything at all else with that pole. If it sees 0.3 to 2.7 kV, then you will want to know what is the potential milliamp that's there, the danger level, as it were. If the kV is greater than 2.7, it becomes a little bit of a moot point worrying about the milliamps. You know that this is a hot site, this is a hot problem, and it needs to be sorted. So you would go straight to checking which of the phases is shorted or effectively broken down to the metal crossarm. So this is a little diagram showing what happens here. So as I said, you've got from the earth point of the instrument, we connect that either to a known good earth if there's one nearby, or we're connecting that to a temporary stake that we've put in the ground. Now, dependent on different, in the UK, which is where I'm most familiar with this, dependent on the board that you're working for or the area that you live in, will depend on the stakes situation. When I worked for Network Rail, for example, we weren't allowed to break ground at all. So if I wanted to put a temporary earth down, what I would do is I'd water with salt water. I would then put a great big metal or quite a reasonable size metal sheet, and I'd park the van on that damp, salty, damp water, and that would become a temporary earth. In the case of most of the boards, they can break ground, and particularly if around the countryside, invariably they may put something a temporary stake into the ground anywhere up to 50-60 centimeters in the ground. The probe we supply is around about 20 centimeters, and it's a handheld. You just basically push it into the ground, and that will allow then you to clip to that and use that as an earth. The other end, what we have here is the probe. So the probe, as I said, is built into an adapted Beaufort rod. So to put that onto the overhead line, onto the cross member, you would actually have a set of Beaufort rods connected at the bottom end, and then you'd hook that over like so and leave that there. As I said, on the display of the unit here, we would use the selector to select steelwork voltage and hit that button there. Hopefully you can all see that. We'd hit that button there, and that then would allow us to see what voltage is present on the steelwork. So for the purposes of today, if the steelwork was more than 300 volts but less than 2.7 kV, we know that we have a insulator that is breaking down, but it's not completely broken down, as it were. So the system would remain live. The protection for that system would recognize there's a fault, and it would indicate at the substation there's a fault, but crucially the system would hold up, and it gives the engineers opportunity to go to site and find where these faults are. Invariably, when a system fault arises on an 11 kV system, the nature of that system is it's a long run. It's going to be a mile, and then anywhere up to 30 miles maybe. Therefore, it's not straightforward to find out where the fault is. It's literally they will drive along, look at the insulators, and or they'll have an idea where they've seen problems recently. Also, it may not be just one insulator that's broken down. It could be several poles that have issues, and together they've given but alone they may even all of them be less than 300 volts. So this is quite a arduous task to find these leaky insulators. So if we were doing a current test, if we, as I said, if we've got the measured voltage is between 300 to 2.7 kV, 300 volts to 2.7 kV, then we would carry out an ISC test to find out what is the prospective short circuit current at this point. So from the menu on the selection point on the display, you would select ISC. The tester will then again measure the voltage, and it will at that point calculate the ISC. Now, if the ISC is less than 0.3 milliamps, then a green light will illuminate, and it shows that the system is, it's not a hot system. It's no 11 kV system is considered safe as such, but it's safe to, for the guys to continue. If the ISC is between 0.3 and 5 milliamps, then an orange warning LED light will illuminate, and it's telling them that potentially the cross member has got a voltage with potential current, and the pole itself will have voltage on it with potential current. we're measuring at the cross arm, which obviously gives you a potential of 5 milliamps or up to 5 milliamps, for example. But it means that as you go higher up the pole, that potential voltage and therefore the potentially short circuit current will become a higher level, and therefore the higher up the pole you go, the more danger you potentially can see. If the IC is greater than 5 milliamp, then the red LED light will light to show danger, because at 5 milliamps, the human body at 5 milliamps or more of energy, that or of current, sorry, is a level which is perceived to be dangerous to human beings, and so therefore if it's detected that, then it will show danger. As I say, the guys working on 11 kV systems will all be aware of the dangers anyway, and will have the appropriate safety equipment, insulated suits, etc. But this is telling them what level of danger is posed before them in this pole. So what we've got here is, you can see the way we've connected the instrument is exactly the same as it was. You've got the potential there where the poles come down, and on there what we've done is use that to select ISC measurement, current measurement, and as I say, at the end of the test it will display accordingly. Stage 4, well, if the ISC was above 2.7, then stage 4 is effectively stage 3. But stage 4 is, we've detected there's a voltage on the cross member. We've detected it's at a level that we need to sort and change the insulator. So at that point, and as I said earlier, these guys are suitably trained, and this won't be done under dead conditions. This will normally be done under live conditions. So at this point, they need to identify which insulator has broken down. So what we do is on the test, we select on the tester phase test on the MCAT Plus. The unit will then communicate with a second probe. So what we have is a second probe that we put up onto, first of all, we'll put it onto phase 1. And it will communicate with that probe, and it will tell you, yes, we're, the two things are communicating wirelessly, and we're ready to carry on. So we take the cone, we hook it over phase 1, and the phase 1 phase angle will be displayed in degrees. And the unit will either come up and say yes or no, that's the phase that's the problem. Because obviously, if the voltage and current that's sitting on that cross arm matches phase 1, that tells you that phase 1 insulator has broken down. But we wouldn't just do phase 1. We'll always do phase 1, phase 2, phase 3. And if the phase angle measured is 30 degrees or less, then the phase is considered to be in phase, and that indicates that's the phase that's broken down. Now, there are occasions where you may have more than one insulator broken down. So you might find that phase 1 and phase 3, for example, both show as in phase. And that tells you then that you need to change both of those phases. But you always test all 3 phases. Never just test. If you test and you find one and you change it, you would still test for the other 2 just to see if there is voltage there, and then that stops you having to mess about bringing the crane back down, bring the crane back up to change another phase. So this is a diagrammatic again of what's going on. So we've still got the unit there with the voltage measurement point there. We've got the earth connected, the pole itself, although as I said, it is an insulator, but it's an insulator that is connected to earth. And here we have the wireless WPC, the wireless phase checker, and the wireless phase checker, in the case of this one, it's on phase 3, and obviously we're at the end of that range. You'd normally start phase 1, phase 2, phase 3, and we'd test that accordingly. So that, essentially, ladies and gentlemen, is the way in which the MCAT is used. It's relatively simplistic, and that's the whole idea of the instrument, is to make that job very, very easy. We're looking at the cross member, we're checking that if there's a voltage there. If we find a voltage and the voltage is below 2.7 kV, we would then check the potential current that's there at that cross member, and if there is a leaky insulator, we then use that wireless probe to identify the insulators. But the unit itself, this is the kind of a second generation of this unit. We took over HVI in 2020, and at that point, the old version of this, there was many components on there that were obsolete, so we were going to discontinue it. We were approached by the Energy Network Association in the UK to bring this unit back from the brink, but when we brought it back, we enhanced it quite considerably. But one of the other applications we have got for the unit is on 33 kV systems. Now, this unit is designed for 11 kV systems, and that's where it would be used at this present moment in time. We may look at doing a 33 kV version or other versions according to voltages, but this unit here at the moment is effectively good to 15 kV. So in the UK, we also have pole mounted 33 kV lines. And on those lines, they have telecom boxes about 2/3 of the way up the pole. Now, we have sold the unit where what we would do is we would take the voltage probe and we would move it all the way up to the pole to just above the telecom box. Now, obviously, if the pole shows no residual voltage on the pole, that means that the guys, the linesmen, know that that pole is safe to climb up onto and obviously work on the telecoms box. If, of course, they find that the pole itself is showing a voltage, then they know that they need to take out, they need to access the telecom box, not on a ladder or climbing. They need to do it via a bucket and lift, as it were. So what does the kit consist? Well, as I said, what we've got is we've got the main box here, which has got the controls, and it's the brains of the tester. We have an earth lead that comes out of here, which connects to the earth. We have the HV probe, which is this probe here, that we use to connect to the cross member. And then lastly, we have this part here, which is the hook that hooks over phase 1, phase 2, phase 3, and communicates with the MCAT, which would identify on the MCAT which phase had broken down, and therefore which insulator is the one that needs to be looked at. And that in essence is it. It's, as I said, we've designed the unit to be as straightforward as it can be. We've designed the unit, to make it very easy to use, and I'm sure everybody here can see quite easily how the unit's working, what it's doing, what the application is, and what can be done.